In this lecture, we are going to continue the study of vector bundles, and in particular, we are going to define fiber maps. Then we will provide some definitions for fiber maps that we are going to illustrate with a particular example, the differential of a map. So we consider two vector bundles, psi1 and psi2. Okay, psi j has base mj, total space ej, and projection pj, and we say that a map from the total space of the first vector bundle to the total space of the second vector bundle is a fiber map over this small f if the following diagram commutes. Okay, what does this mean? In particular, it means that the image by this capital F of a fiber for the first vector bundle is contained in a fiber for the second vector bundle. And indeed, the image of the fiber over X for the first vector bundle by capital F is contained in the fiber for the second vector bundle associated to the point small f of X, okay? And this happens for every X. Now let us provide some definitions. Okay, we say that capital F is a morphism of vector bundles if the restriction of capital F to every fiber is indeed linear. We have to realize that the restriction of F to the fiber for the first vector bundle of X is indeed a map from such a space to the fiber for small f of X of the second vector bundle. And since this is a map between vector spaces, we can require that it is linear. And indeed, by definition, if it is linear for every X in M1, then we say that our fiber map is indeed a morphism. Okay? So a morphism preserves the linear structure. It's a map, it's a fiber map between the vector bundles that preserves the linear structure. Right? Now we can define a monomorphism. It's a morphism of vector bundles. So the restriction of capital F to the fibers is a linear map for every fiber, but we're going to require that such a linear map is injective for every fiber. If this happens, we say that capital F is a monomorphism of vector bundles. If instead of requiring these linear maps to be all injective, we ask them to be all surjective, then, and of course capital F is a morphism of vector bundles, then we say that capital F is an epimorphism of vector bundles. If we have a morphism of vector bundles such that these linear maps that are induced in the fibers are all isomorphisms, then we say that our fiber map, our morphism, is a bimorphism, okay? We say that it is an equivalence if it's a bimorphism that covers a diffeomorphism. In other words, if it's a bimorphism such that this map over here, small f, is a diffeomorphism, and it's an isomorphism if it is a bimorphism covering the identity. In other words, if it's an isomorphism such that these two M1 and M2 are the same, and the map small f over here is indeed the identity map. Okay, so now we can consider an example of fiber map, an example of morphism of vector bundles, right? We consider two manifolds M and N and a differentiable map F, we can consider, for instance, that all of them are C infinity. And here we have the natural projection associated to the tangent fiber bundle. Okay, and here the same for the tangent space of N. And we can consider over here the differential, right? This diagram is commutative, so the differential of F is a fiber map. If we looked at the restriction of this map to a fiber, in other words, to a tangent space of M at a point, right? This differential is a linear map for every point x. So the differential of F is a morphism of vector bundles, right? Now it is interesting to check out when this differential is a monomorphism, an epimorphism, and so on. Okay, the differential of F is a monomorphism of vector bundles if and only if these differentials of F at every point are injective. But that's exactly the condition of F being an immersion. Okay? The differential of F is an epimorphism. Okay? If the differential of F at the point x is surjective for every x. In other words, if F is a submersion. So we can translate these new properties that we defined for fiber maps in terms of properties that we know well for the map F. Obviously, the DDF is a bimorphism if and only if it is a monomorphism and an epimorphism. So if and only if F is an immersion that is also a submersion. Okay. Another question is when DDF is an equivalence. But of course, in order to be an equivalence, it has to be a bimorphism over a diffeomorphism. So we need that F is a diffeomorphism. Very good. But if F is a diffeomorphism, then DDF is an equivalence, because all these maps over here are indeed bijective. They're all linear isomorphisms. So this is also an equivalence. And DDF is an isomorphism. Sorry. But if it is an equivalence over the identity map, so we need that F is indeed the identity map of M. And obviously, if F is the identity map, DDF is also the identity map and it's an isomorphism. So we were able of translating the properties that we just defined for fiber maps in the particular case of the map DDF in terms of properties that we already know, properties of differentiable maps. Okay, what we want now is defining trivial vector bundle. So we're going to consider this vector bundle over here, whose base is M. M is a manifold. The total space is the Cartesian product of M and Rn, and P1 is the projection on the first component of n times Rn. This is a trivial vector bundle. Is the model of trivial vector bundle, and we say that a vector bundle of dimension n is trivial if it is isomorphic to the model of trivial vector bundle, right? In that case, we are also going to consider that such a vector bundle is trivial. And we are going to say that the isomorphism between these two vector bundles, the PEM and then the trivial one, is the trivialization of the first vector bundle. An interesting question is knowing whether there exist manifolds such that every vector bundle over them is a trivial vector bundle. Indeed, we will see that this is the case and that every vector bundle over a contractile manifold is always trivial. And in order to prove such a theorem, we will introduce an homotopy extension theorem. Thank you for your attention.